The date is January 12th, 2026. If you've been following the celestial anomaly known as 3I Atlas, you know we've been waiting for the other shoe to drop. Well, it just did. And frankly, the data we are looking at tonight doesn't just challenge our models, it effectively breaks them. Let's look closer at the data coming in from the Hubble Space Telescope. New images taken just 5 days ago, on January 7th, have confirmed a feature that astronomers had only whispered about until now. We are looking at a high-resolution composite of the interstellar object, and unmistakable in the frame is a sharp, coherent structure, a powerful, narrow jet pointing directly toward the Sun. Now, in the context of standard cometary physics, this shouldn't be there. Comets, as we know them, are dirty snowballs that heat up as they approach the inner solar system. They outgas, releasing dust and volatiles that form tails. But those tails are dictated by two fundamental forces: solar radiation pressure, literally the pressure of sunlight pushing against dust particles, and the solar wind, a stream of charged particles flowing outward from our star. Both of these forces work to blow cometary material away from the Sun. That is the rule. It is a rule that has held for every comet observed since the dawn of telescopic astronomy. 3I Atlas is breaking that rule. This new jet is an anti-tail in the most extreme sense. It is moving straight into the teeth of the solar wind, fighting upstream against the radiation pressure. And it is winning. The structure extends roughly 400,000 kilometers from the nucleus. To put that in perspective, that is a jet of material stretching the entire distance from the Earth to the Moon, maintaining its cohesion against forces that should be scattering it into a diffuse cloud. This contradicts what we previously thought about the object's activity mechanisms. When we first saw hints of this in the July 2025 data, there was a hope that it might be a projection effect, a trick of the light caused by our viewing angle. That hope is now gone. This is the moment where I should mention that if you want to stay ahead of this rapidly evolving story, you should verify that you are subscribed to the channel. We are tracking this object daily, and as we get closer to the March events, the updates are going to become critical. Using the Larsen-Cicconnina rotational gradient filter, an image processing technique designed to bring out subtle contrasts in the coma structure, astronomers have revealed that this sunward feature is actually the dominant component of a complex triple jet system. But unlike the other fainter jets, this sunward spike is tightly collimated. It isn't fanning out, it's a beam. The stability required to maintain a structure like this, 10 times longer than it is wide, while plunging toward the Sun, implies an intrinsic velocity and a material density that we simply do not see in natural evaporation processes. So, what does this actually mean? It means we have to discard the passive comet hypothesis. A passive body does not behave this way. If this were simple sublimation, ice turning to gas, the gas would expand isotropically, or at least in a broad cone sunward before being swept back. What we are seeing here is an outflow that is focused. It suggests a nozzle. It suggests a constrained release of energy or matter that is impervious to the standard environmental pressures of the inner solar system. The brightness of the jet is another puzzle. At this distance, it is inexplicably luminous. If it were made of standard dust, the solar wind should be stripping the smaller, brighter particles away, leaving only heavier, darker grains that would result in a faint, diffuse tail. Instead, the feature remains brilliant and distinct. This suggests the particles within the jet are either incredibly heavy, resistant to radiation pressure, or they are being replenished at a rate that is frankly staggering for an object of this size. Here is the crucial detail that makes this even more unsettling. The jet was already visible in July 2025. This means the phenomenon is persistent. It isn't a momentary outburst or a crustal fracture caused by thermal stress. It is a continuous, stable state of the object. We are watching something that has been on for months, maintaining a precise orientation relative to the Sun despite the object's movement through space. As we stare at these images, we have to ask, what mechanism keeps a jet pointing at the Sun? In a natural scenario, a rotating comet nucleus would spray material in a spiral pattern, like a garden sprinkler. To have a straight, sunward-pointing jet from a rotating body requires the source of the jet to be effectively locked to the sub-solar point, the spot on the surface where the Sun is directly overhead. This implies either the object isn't rotating, which we know is false, or its rotation is weirdly specific. This leads us directly into the orbital dynamics and the spin state of 3I Atlas, where the coincidences stop looking like accidents and start looking like geometry. Because when we analyze the wobble of this jet, we don't just see chaos. We see a distinct pattern that points to an impossible alignment. We need to talk about the odds. As we established in the previous chapter, the existence of a coherent, sunward-pointing jet on 3I Atlas is already a significant violation of standard cometary behavior. But if the morphology of the object is baffling, its geometry is statistically terrifying. Let's look closer at the data concerning the object's rotation. By tracking the subtle wobble or precession of that sunward jet over the last several months, astronomers have been able to reconstruct the spin axis of the nucleus. Imagine the object as a spinning top. The axis of that spin isn't pointing randomly into space. Measurements indicate that the rotation axis of 3I Atlas is aligned with the Sun to within about 7 degrees. This is an extremely unlikely configuration. In the chaotic gallery of interstellar objects and comets, spin axes are distributed randomly. There is no physical law that demands a newcomer to our solar system align its pole with our star. In fact, tidal forces from the Sun are far too weak at these distances to have torqued the object into this alignment during its brief passage. It presumably arrived this way. But the coincidence goes deeper. Not only is the pole pointing at the Sun, but the object's trajectory, its path through space, is also closely aligned with the ecliptic plane, the flat disk where Earth and the other major planets orbit. Most interstellar objects, like 1I/Oumuamua or 2I/Borisov, come from random inclinations. They drop in from above or below the solar system, cutting through the plane at steep angles. 3I Atlas is different. It is sliding in almost perfectly flat, moving within the same traffic lane as the planets. When you combine these two factors, a pole pointing at the Sun and an orbit varying little from the ecliptic, the combined geometry is statistically improbable at better than 1 part in 10,000. So, what does this actually mean? In probability theory, When you see a 1 in 10,000 chance event, you have two options. Option A, we just won the cosmic lottery. It happens. Option B, the underlying assumption of randomness is wrong. If the alignment isn't random, it implies a constraint. It implies that the object's orientation is coupled to its trajectory, or perhaps coupled to the sun itself. This contradicts what we previously thought about interstellar debris. Debris is chaotic. Tumbleweed in the wind doesn't orient itself aerodynamically unless it has a fin. 3I Atlas is acting like it has a fin. The specific alignment of the rotation axis ensures that one hemisphere of the object is essentially in permanent daylight, while the other is in permanent night, a summer solstice configuration that never ends. This maximizes heating on one pole. If this were a natural comet, that constant heating could explain steady outgassing. But remember the jet. The jet is stable and narrow. If the pole is pointing at the sun and the jet is coming from the pole, then the jet is acting like a thruster, firing along the line of motion. The stability of this configuration is key. If the object is non-spherical and light curves suggest it is elongated, torques from outgassing usually cause the spin to accelerate or drift. We call this the Yorp effect. Yet, 3I Atlas maintains its sunward stare. This connects to the phantom trail that we discussed earlier. The Larsen-Sekanina filter revealed a triple jet structure. If the main jet is the polar outflow aligned with the sun, the other two jets might be secondary vents, but the dominant feature is that anti-tail. The geometry essentially turns 3I Atlas into a stabilized platform. It is keeping its eye or its nozzle fixed on our star. This brings us to a question I want you to answer in the comments below. At what point does a series of statistical improbabilities stop being a coincidence and start being evidence? We have a physics-defying jet, and now a geometry that defies the odds of random injection. Is there a threshold for you where natural origin stops being the default answer? Let me know what you think. The precision of this alignment becomes even more critical when we look at where 3I Atlas is going next. It isn't just passing through, it is threading a needle. As it recedes from the sun, it is not heading into empty space. It is on an intercept course. We are watching a set of initial conditions, spin, orbit, jet orientation, that seem perfectly tuned to facilitate a specific event in the outer solar system. The object is heading toward the domain of the king of planets, and the timing is practically synchronized. Are we looking at a gravity assist or something more complex? The alignment with the ecliptic plane makes a close encounter with a planet much more likely than if it came in at a steep angle. And sure enough, the calculations show a rendezvous that is shocking in its intimacy. And this leads us to the wildest hypothesis currently circulating circles in the astrophysics community, the Eupheme connection. There is a scenario, improbable, theoretically possible, but highly suspicious, where 3I Atlas could interact with this region to deploy or deposit material. If the object were to eject fragments during this passage, or perhaps separate into multiple bodies, the dynamics change. We are looking at a Hill radius event. This is the specific term for an interaction right at that gravitational boundary. If 3I Atlas is a coherent body, it passes on. But if 3I Atlas is a container or a stack or a mothership, Let's use the word. Then this boundary is the perfect drop zone. The timing is what keeps scientists up at night. The alignment we discussed in Chapter 2 essentially set up this trajectory. If the jet we discussed in Chapter 1 is a propulsive maneuver, it may have been a course correction. A correction to ensure this specific date with Jupiter. Imagine you are skipping a stone across a pond. The stone is 3I Atlas. Jupiter is the other side of the pond. The speed is 66 kilometers per second. If a chip flies off that stone at just the right moment, with just the right kick, it doesn't cross the pond. It sinks. It starts orbiting. But here is where the physics puts up a stop sign. We have to talk about energy budgets. To turn a 66 kilometer per second flyby into a capture orbit requires a massive change in velocity, or delta V. This connects to the sheer scale of the challenge. A natural fragmentation, a rock splitting from heat or tidal stress, imparts a small kick, maybe a few meters per second, maybe hundreds if it's an explosive sublimation. But we are talking about kilometers per second of difference required to settle into a stable orbit around Jupiter from such a high approach speed. We are setting the stage for an impossible physics problem. We have an object that shouldn't be jetting sunward, aligned in a way that shouldn't be random, approaching a specific boundary in the Jovian system. As March approaches, all eyes, arguably, shouldn't just be on the object, but on the empty space near it. We are waiting to see if 3I Atlas leaves something behind. As we established, 3I Atlas is screaming toward Jupiter at 66 kilometers per second. We defined the Hill radius event as the moment it grazes Jupiter's gravitational influence. Now, we have to break down the capture problem because this is where the hard math contradicts the idea of a natural origin. Let's look closer at the data regarding escape velocities. Jupiter is massive, the vacuum cleaner of the solar system. Its gravity is immense, but even Jupiter has limits. The escape velocity near Jupiter's surface is very high, about 60 kilometers per second. But 3I Atlas isn't skimming the cloud tops. It's passing 53 million kilometers out. At that encounter distance, Jupiter's escape velocity is weak, merely 2.2 kilometers per second. This is the speed limit for being a moon. If you are moving faster than 2.2 kilometers per second relative to Jupiter at that distance, you aren't a moon. You are a visitor. You fly by. 3I Atlas is moving at 66 kilometers per second. Do the subtraction. 66 minus 2.2. The object is moving roughly 64 kilometers per second, too fast to be captured by Jupiter's gravity alone. For any part of 3I Atlas to stay in the Jovian system, it needs to lose that 64 kilometers per second of relative speed instantly. This contradicts what we previously thought about fragmentation events. In a natural breakup, say, a comet spinning itself apart, or cracking from thermal stress, the pieces drift away from each other gently. They might separate at 5 meters per second, maybe 10. In the most violent, explosive, volatile outbursts ever recorded, fragments might get a kick of 1 or 2 kilometers per second. We need a kick of 60 plus kilometers per second. There is no known natural mechanism for a small, icy body to explode with enough force to halt a fragment dead globally in its tracks against a 66 kilometer per second approach, without vaporizing the fragment in the process. Kinetic energy scales with the square of velocity. To accelerate a fragment backward at 60 kilometers per second requires an energy release comparable to a tactical nuclear detonation, focused entirely in one direction. So, what does this actually mean? It means if we see a new moon appear around Jupiter after March 17, 2026, we are not looking at nature. Nature doesn't have a braking thruster. Nature doesn't perform orbital insertion burns. If the object were to eject fragments during this passage and one of them becomes gravitationally bound, that fragment had to execute a high-energy maneuver. It implies a precisely directed velocity change, an impulse that cancels out the approach speed perfectly to drop the fragment into a stable orbit. And remember the anti-tail from Chapter 1? That sunward jet? It proved the object has a mechanism for directed outflow. It proved the object can maintain a stable axis. If that same mechanism is capable of a high-thrust event, or if the jet we saw was actually a braking burn performed early to fine-tune this arrival, then the picture becomes coherent. This connects to the concept of the Bracewell probe, or von Neumann probe, theoretical autonomous spacecraft sent to monitor other star systems. A probe doing a flyby might drop a sub-probe. To drop a sub-probe at high speed, you need a high-impulse separation. The impossible kick required to leave a calling card at Jupiter is the smoking gun. If 3I Atlas leaves the solar system intact, but Jupiter gains a new satellite, the laws of celestial mechanics tell us that the new satellite did not get there by accident. It would have to be placed there. The sheer improbability of the alignment from Chapter 2 combined with the impossibility of natural capture physics from Chapter 4 creates a corner that the natural object hypothesis can no longer maneuver out of. We are forced to consider the alternative. The appearance of a new Jovian moon after this encounter would therefore be extremely difficult to reconcile with a purely natural origin, and would represent a potential technological signature. As we established in the previous chapters, we are looking at a sunward jet that shouldn't exist, an alignment that defies statistics, a targeted flyby of Jupiter, and a capture physics problem that rules out natural fragmentation. The evidence has piled up. Now we reach the final verdict. Together, the persistent sunward anti-tail, the improbable geometric alignment, and the upcoming close passage through Jupiter's gravitational domain make 3I Atlas one of the most anomalous interstellar objects ever observed. It makes Oumuamua look like a simple rock. We are staring at a potential technological signature. The term technological signature is specific. It doesn't mean we have a picture of a Hull number. It means we have data that cannot be generated by the background noise of the universe. The 400,000-kilometer jet pointing upstream? That's a signature. The one in 10,000 alignment? That's a signature. A captured moon appearing at Jupiter in March would be the signature. So, what happens next? March 2026 offers a rare and potentially decisive test. This is not a drill. We have assets in place. The encounter will be monitored both by Earth-based telescopes and by NASA's Juno spacecraft in orbit around Jupiter. Juno is the trump card here. The spacecraft has been orbiting Jupiter since 2016. It is aging, bathed in radiation, but its instruments are active. NASA has already adjusted observing schedules. Juno won't be close enough to 3I Atlas to see surface details. Space is too big, but it is perfectly positioned to detect the aftermath. If 3I Atlas dumps energy, if it fires a thruster to slow a probe down, Juno's WAVES instrument and magnetometers might detect the plasma disturbance. If a new moon appears, Juno's camera, JunoCam, can hunt for it in the weeks following the pass. This contradicts what we previously thought about our readiness. Usually, these objects come and go too fast. This time, we are waiting at the finish line. Here is the crucial detail regarding the verdict. If nothing happens, if 3I Atlas flies by Jupiter, stays intact, and heads back out into the void without leaving a trace, then we are left with a massive mystery, but a natural one. We will have to rewrite the books on cometary jets and statistical alignments. It will be an exotic comet. But if something stays behind, humanity changes. We move from a species guessing about life in the universe to a species studying an artifact left on our doorstep. The impossible kick, described in Chapter 4, becomes the proof of engineering. We are weeks away from one of the most significant moments in astronomical history. Whether it is a freak of nature or a messenger from the stars, 3I Atlas has already earned its place in the history books. If you enjoyed this deep dive into the unknown, please hit the like button. It tells the algorithm that you want more hard science and less fluff, and it helps us keep tracking these mysteries. Until March, keep looking up.